assessment of the ultrasound.
Okay. Good morning, everybody. As Dr. Palumbo said, I've been radiologist at FIPAP for almost 20 years. And I have a special interest in 3D ultrasound and in programs for automatic follicular monitoring. I'll present 2 talks during this course, and in the first one I will try to give you some hints to achieve good results in 3D imaging. As this is a quite hard topic, I think it's a good thing that Peter and Marcelo talked before me. We are going to review some of these topics and fix them. This is, as I said, a hard topic, but I will try to do it easier as possible. This is what we are going to see. In the beginning, we are going to review briefly some physics to understand how the ultrasound works and what things can affect image quality. Then we are going to know what the information shown in the screen means and how to optimize to the image. Finally, we will review briefly some of the most important post-processing tools in 3D. Most of them you have seen before in Dr. Palumbo talks and Marcel and Peter talks. Well, medical ultrasound is based on the use of high-frequency sounds for aiding the diagnosis and treatment of patients. These waves, this frequency ranges between 2 and 15 megahertz and travels through tissue in the form of a wave with areas of compression and decompression. It gives us real-time images resulting from the reflection of these echoes in the organ surfaces that are captured by the transducer. The ultrasound wave is defined by 3 parameters. We have the wavelength, that is the distance where one cycle occurs. It's the same as the distance between the beginning and the end of one cycle. We have the amplitude, that is the maximum depletion of the wave, and we have the frequency. The frequency is the number of cycles in 1 second, and it's expressed in hertz. In this example, we have 2 ultrasound waves. The orange one has a short wavelength and a high frequency, while the blue one has a wide wavelength and a low frequency. And these 2 waves are going to have different penetration because they have different attenuation coefficient. The attenuation coefficient is a parameter that measures the decrement of the ultrasound wave amplitude while they go through tissue. And when we have an ultrasound wave with a high frequency, the penetration will be low because the attenuation coefficient is high. While when we have a low frequency wave, the attenuation coefficient will be low and the penetration will be high. That's because the penetration is inversely proportional to frequency. This is important when we are going to choose a probe. We have to think about what penetration we need and then look for the range of frequency of the probe that normally is expressed on them. Well, when we are going to do an ultrasound, what we want is the best image resolution. Image resolution, we have on one hand, we have the spatial resolution that has 2 aspects, axial resolution and lateral resolution. The axial resolution is the ability to distinguish 2 objects that are in the same along the way of the beam axis, while lateral resolution is the distance side by side of 2 objects in a perpendicular plane to the beam axis. Resolution can be improved by increasing the frequency, reducing the beam width by focusing, and also increasing the number of lines per frame and using multiple focal depth. But be careful because these strategies of increasing the number of lines per frame and using multiple focal depth can affect temporal resolution. On the other hand, as I said, we have the temporal resolution. This is very important when we are studying moving objects like vessels or a heart. And the human eye needs at least the image to be updated at least 25 times per second to appear continuous. There are several factors that can reduce the temporal resolution, and the first one is the line density. If we use several lines of scans, we will obtain a better resolution, but the temporal resolution will decrease. Temporal resolution is the same as frame rate. You can call it both. We can, the number of focal points and the depth also decrease temporal resolution, and the Doppler reduces the frame rate by a half. So when we are going to use Doppler, try to increase at maximum the temporal resolution, because it's going to decrease when you apply the Doppler. In conclusion, we must adjust our parameters to have the best spatial resolution with the highest frame rate possible. Now we are going to show you what are we going on the screen. On the left side we have this small white triangle here. The newer devices doesn't have this triangle because this is the focal zone. Now in the newer devices it's adjusted automatically, and you have to place it in the point that you want the maximum resolution. Then we have the green mark. This is corresponds to the notch on the probe. So if you have this mark on the right of the screen and you turn the probe to the right, the notch of the probe to the right, then the screen of the right side of the patient would be on the right on the screen, and vice versa. Now this is the information we have in the upper right corner. We have here a lot of things. We have the name of the probe, we have the frequency, the depth, the angle, the name of the protocol we are using, if we are using harmonics, high, medium, low penetration. We have the contrast map, the gray map, filter frame, the enhancer edges, and here we have if we are using speckle reduction or compound imaging. This information is the thermal index for soft tissue and bones, and the mechanical index. So how are we going to optimize our 2D image? In our ultrasound machine we are going to have different protocols for depending on what we are going to study. But we have to know that there are parameters that we can adjust easily to improve our image. The automatic optimization, I think, is a good starting point because it adjusts automatically the gain and contrast of the image. It analyzes the tissue and attempts to give you the best image quality as possible. Then we have the angle. We have, by adjusting the angle to the region of interest, we are going to increase temporal resolution, as I said. Then we have the depth. Remember that the region of interest have to be placed in the center of the screen. And the focus, not in the newer devices, as I said, put the focal plane in the point that you want the maximum resolution. And this is the gain and temporal gain control that is here. The gain increases the overall brightness of the image, and with the TGC we can compensate the decrement of the signal in depth. But remember that this increased the signal of the echoes, but also the background noise. About the dynamic range, this is the range of amplitude of the ultrasound signals from the highest to the smallest one that the device can detect. So if we have a wide dynamic range or a high dynamic range, we will have a high grayscale values and the image will look softer. While if we have short dynamic range, the image will appear more contrast. The tissue harmonic imaging, HI, is here. diminish the artifacts, sending and receiving signals at two different frequencies. The problem with the harmonic is that sometimes when we are studying deep structures, the signal can just disappear. So in these cases that you have very dark or very poor signal, we have to lower the harmonics or even turn it off. Compound imaging or cross X-beam or X-beam CRI also reduces artifacts because it sends images, it sends ultrasound signals in different angles, steering angles. Classically, the probe sends a single signal perpendicular to the head of the probe, and then it listens to the echo. But in this case, it's going to send different signals with different angles and then listen to the echo from different point of view, so it decreases the artifacts. The speckle reduction or SRI, and this is the compound imaging here, and speckle reduction also decrease the noise because it differentiates between the strong and the small signals and enhances the strong ones and eliminate the noise. This is the two last parameters that are aided by artificial intelligence, augment and ultra high definition. They improve the definition of tissue interfaces and highlights the relevant anatomic details. Are here. Okay. Once we have the best image quality in 2D as possible, we can proceed with the acquisition of the volume. We have to place the probe in the middle of the region of interest, adjust the 3D box, adjust the angle, and stay still while the acquisition is going on. During the scan, several parallel images are going to be acquired and will be represented at the end in a multiplanar view. So remember that at the moment of the acquisition, we must consider that time increases with the angle and with the image resolution, as Peter and Marcelo tell us. This is important when we are studying moving structures, so we use mid or high for obstetrics and very high for gynecology, and always adjust the angle to the region of interest. 3D imaging has several advantages that are widely known and demonstrated, like it gives you the opportunity to revise the study when the patient has left. You can ask a colleague for a second opinion without disturbing the patient. And you can use the post-processing tools to enhance your findings or to aid in the diagnosis. This is the multiplanar view we have seen before. And first of all, I would like to remember how to navigate in this multiplanar view in a different way that Peter and Marcelo told us, so maybe we can fix this concept. To do so, we are going to start with the coronal plane and we will rotate it in the different axes. So if we have the coronal plane and we rotate the uterus in the X plane, we will obtain an axial view. And this is because the uterus will do the same movement as a roast chicken does. If we have the uterus in the coronal plane and we rotate it in the Y-axis, we will have the sagittal view, because the uterus will do the same movement as a ballerina in a music box does. And finally, if we have the coronal plane of the uterus and we turn it in the Z-axis, the uterus will move like the hands of a clock. So when we are reconstructing 3D imaging in the multiplanar view, we have to think how we want the image to move, like a roast chicken, like the ballerina, or like the hands of the clock. And if you finally get lost, you always come back to the beginning, pressing in it. Another tool we have is the HD Live. Most of the current surface reconstruction use the frontal illumination for the render mode, and it gives the image to appear flat. In this case, you can move the source of the light, and when you illuminate the image from the side, the three-dimensional impression increases significantly. With the silhouette, you also can adapt light brightness and shadow softness. Vocal, its main application, I think now is in oncology, to measure tumor volumes, to do the follow-up after treatment. In reproduction, at the beginning we used it before applying the sono-ABC, but now it's not necessary anymore. And maybe we can use it to measure the ovarian volume or the endometrium or subendometrial vascularization. This is an example of a vocal of the endometrium. And sono-ABC is a specialized software that automatically detects hypoechoic structures inside the 3D volume. It calculates its number, the three diameters, the mean diameters, and the volume of each follicle that are represented in the report. And they are also color coded, so it can be easily identified in the reconstruction. Until now, we had the sono-ABC antral for the study of the antral follicles and sono-ABC follicle. But now with the sono-ABC follicle 2.0, this is useful for both, to study antral follicles and preovulatory follicles. The multi-slice view, the data are represented as parallel slices, like the CT scan, for example. You can select the number of slices, you can select the distance between slices. This is the Omni view that we have seen. With this application, you can design the plane of visualization on the volume. You can also increase the thickness of the plane. And this is very useful when we are trying to delimitate ill-defined structures. You can do this in a dynamic way with the uterine trace that we have seen before. This is another example. This is just because I think it's a very beautiful image. It's the fibroid mapping during a sonohysterogram, but we have a talk in this topic. This is the VCI. However, it looks like a multiplanar view. Each of the planes are calculated with the total information of the volume. The magic cut, with this application we can cut the structures that are in front of the region of interest. And finally, the radiant, that we can use it alone or combined with the ultra high definition or augment. It uses artificial intelligence also and highlights the edge and contours of the structures and the text interfaces. Here I have an example. You can put low radiant, medium radiant, or high radiant. I think it's very nice, for example, for adenomyosis to demonstrate it very nice. So, 3D ultrasound opens a wide range of possibilities to improve the diagnosis in gynecology and obstetrics. It's true that it requires a learning curve for both the acquisition and the post-processing. The quality of your 3D image depends on your skills on 2D, so it's not easier. Remember to use the specific protocol depending on what you are going to study, and to adjust the basic parameters like depth, angle, focal zone if you have this possibility, or gain. In difficult cases, remember that there are other parameters that you can modify, like the density lines, use the SRI, cross-beam imaging, and all of them. And always mind the frame rate. more when you are studying moving structures. So thank you very much. I hope this has been an inspiring talk that encourages you to practice and don't leave you too tired for the rest of the course. Thank you.